Every standard metro network and localized enterprise loop operates on a very specific physical thread. They rely heavily on point-to-point single-mode fiber links, stretches of pure glass that routinely span anywhere from 80 to 110 kilometers. From the outside, this macro-level infrastructure looks highly efficient. Inside the glass, however, light has to navigate a microscopic physical obstacle course. The first barrier is something physicists call the fiber attenuation coefficient. Even in the clearest optical glass, light naturally degrades and scatters as it travels over vast distances. That natural decay is then compounded by environmental and man-made hurdles. Across a 100-kilometer span, minute connector losses and slight physical bends in the cable drain the signal even further. This creates a critical engineering problem if you want to expand the network. Adding complex distribution components, like high-loss optical splitters, onto an unverified fiber line will instantly mask those underlying flaws. Before network expansion can begin, engineers have to isolate the bare physical glass and mathematically prove its structural integrity. That specific task is why the Conway Max 600 M1 exists. It operates as the baseline workhorse engineered strictly to characterize these standard single-mode point-to-point networks. To map the glass, the M1 systematically fires rapid, highly calibrated bursts of light directly down the core of the single-mode fiber. The M1 deploys light at two wavelengths, 1310 and 1550 nanometers, optimized for long-distance glass penetration. When these forward-moving waves hit a microscopic impurity, a fracture, or a bad connection, a fraction of light reflects backward. This is called backscatter. Sending light down the pipe is easy. The difficulty comes from how faint those backward-traveling echoes become after bouncing off a flaw 110 kilometers away and returning to the source. The testing device has to pull those weak, returning optical echoes out of the ambient systemic noise inherent to any electronic system. The true utility of the M1 is its extreme sensitivity. It is built to catch and isolate microscopic reflections across vast spans of geography. Engineers measure a device's ability to hear those faint echoes using a metric called dynamic range. This chart maps signal strength over distance. A dynamic range of 32 and 30 decibels creates a strict floor, catching faint return signals before they fade. This high signal-to-noise ratio clears away static, distinguishing actual physical flaws from random electrical noise. The M1 software takes those clean spikes of data and translates them into a highly accurate, distance-based physical map of the entire cable run. Different physical anomalies reflect light differently. Specific echo patterns tell the software exactly where a macro bend, a tight physical curve, is stressing the glass. Different echo signatures allow engineers to evaluate splice quality, showing exactly how well two separate glass cables were fused together at a junction. Finally, the M1 aggregates all of this backscatter data to measure the total optical return loss across the entire 110-kilometer link. It renders a centimeter by centimeter topography of an entirely invisible physical environment. With the microflaws mapped, engineers can zoom back out and approach the macro scale of local access rings and distribution networks with confidence. They now have a mathematically proven baseline. They know the exact structural realities of their raw physical infrastructure before a single piece of complex hardware is added. This map shows the crucial architectural boundary line right before high-loss splitters are inserted into the access ring. Because the verified trunk line is proven solid, engineers safely branch out through complex splitters, knowing the new hardware isn't masking upstream faults. The Conway M1 acts as the ultimate gatekeeper for standard single-mode point-to-point networks. Enterprise infrastructure and high-speed distribution loops can only support immense data loads if the glass beneath them is structurally flawless. By meticulously mapping the unseen topography of that glass, the M1 secures the physical foundation required for all subsequent digital expansion.